So this is our first lecture in Thermo 2. This is our textbook that we're using, the same one you used in Thermo 1. You covered the first 6 chapters in Thermo 1. We're picking up in chapter 7, and then you were introduced to or covered the introductory parts of chapter 8 with vapor power cycles, chapter 9 with gas power cycles, and chapter 10 with refrigeration cycles. But we will cover those chapters in detail. And where do we start? Chapter 7. I encourage you to read the title of the chapter of the book that you're in. I purpose to follow the book. You will notice there's some things that I do as an instructor to go all the way back to when I was sitting in a seat in a classroom like yours, and it bugged me when an instructor asked me to buy a book and then ignored it. I don't. I adapt my teaching. I adapt the terminology I use. I adapt the presentation of material to the book that I asked you to buy. I work hard to use that terminology, those symbols, so you don't get too confused. But anyway, in chapter 7, I really encourage you, look at the title. What's the title? Read it. Exergy analysis. Look at the main sections. There's a word that's repeated. Exergy. Exergy. Exergy, 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 and exergetic. Come on. What's the focus of this chapter? A misspelled word. It should have been energy. No, it's just one letter different, but it's a new term. It's a new term, a new concept. It's closely aligned with energy. That's why they have it closely with the spelling of energy. Notice that they're going to have it for a closed system. They have it for a control volume, open system. Hey, that's what we've been doing in Thermo 1. Open system analysis, closed system analysis. And then we'll talk about some efficiencies. Hey, we had turbines, we had pumps, we had compressors. Yep, and we'll revisit those and talk about now an exergetic efficiency instead of an isentropic efficiency. Exergy is simply a new property used in thermodynamics. Let me ask you this. With a piece of paper, can you make a list of properties that you used in the previous class, thermodynamics? Thermo 1, or if you're repeating this class, great. Thermo 2, hopefully you're not. But make a list of properties. Start off with the big ones. I'm going to pause, walk around, see how you do. So when a student gets bogged down in solving a problem, usually this is one of the things I help get them unstuck. I say, look, you're talking about a process, starts at initial state 1, end state 2, right? So why don't you think, okay, initial state 1, final state 2, just list all the properties that you know about that state at state 1. They say, okay, P1, T1. Don't forget those. Pressure, temperature, they're kind of like the foundation, the beginning. And then you had this one. What is that? Specific volume. Some people were not accustomed to specific volume before they took Thermo 1. They were probably more accustomed to that term. What is that term? Mass density. What's the relationship between mass density and specific volume? Reciprocal. That's all. So the inverse of the mass density is the specific volume. Then the next one is U1, then H1, S1, and then you can go P2, T2, V2, U2, H2, S2, and often making a list like that really helps you. Now, somebody said, well, I had cap V as volume. Okay, put it on a per unit mass basis, divide by mass, and turn it into specific volume. Or cap U, that's true, that's a property, but divide it by the mass, and then you get the lowercase u. So this is a pretty good list right here. At the end of this list, we're going to have E at state 1, E at state 2. It's exergy. Now, just like you had something that's used when it's a closed system, energy balance, internal energy, you had another property, and it was a very hard concept in Thermo 1 for an open system, and students still will ask me, why do you use H here and U there? Why? I'm confused. How do I know when to use H and when to use U? It's really the flow work is included with U, and then it's H. So what is H? H is simply U plus PV. What is this PV term? The flow work term. And that's the correct term to account for the flow work when it's going across the boundary. All right, a little review of Thermo 1. But just like that, we're going to have a closed exergy on a per unit mass basis. And then we'll have EF1. Oh, this is where it really gets tricky, because you were accustomed to, somebody says, I want you to give me V sub F. I want you to give me U sub F. I want you to give me H of F, S of F. You say, no problem. You're not trying to confuse me. You're not asking for V sub G. No, V sub F. How about U sub G? No, I want U sub F. How about H of G? No, that's different. And then S of G. But what does all the subscript F mean and the subscript G mean coming out of Thermo 1? Saturated liquid for the subscript F, saturated vapors for the subscript G. That comes from the foundations or the beginnings of thermodynamics and out of the German language. You can go research it. Okay. Now, you look at this. Aha! Exergy for saturated liquid. No. Ooh, professor, that's why I might fail this class. The confusing notation and all that. Sorry, you just have to live with it, right? Okay? That means flow exergy. That's what the subscript F will be on that lowercase e for exergy. It's flow exergy at state 1, and then if you have it exiting at a different state out of a control volume, you could have it. But we're getting a little ahead of ourselves, but I'm trying to point out the slippery points, those conceptual difficulties which you'll struggle with. And if I can repeat it often enough, it'll help you. All right. So this is just a new property. The question is energy is defined as, and these are very short definitions, so no definition here on this page is perfect. But in 4 or 5 words, is it the ability to do work? Is it the strength exerted to accelerate? Is it the ability to make something happen? Is it the measurement of sequence of events? The measurement of sequence of events? Or is it the resistance to acceleration? So you just give me your best answer. What is this term energy? Not exergy, energy. Of course, I'm trying to put a tough question to you to help you, because the obvious answer is wrong. I need to stop this, and then we'll go ahead and look at the poll. Okay, most of us fell for the bait. Yep, most of us fell for the bait. Ability to do work. All right, if I have something hot, a chunk of metal that's hot, and I put it into an insulated container, where that insulated container contains a liquid, and it's cold initially, and I sit there and wait for a long time, what happens to the hot chunk of metal? It cools down, it becomes warm. What happens to the liquid in there that was initially cold? It heats up, it becomes lukewarm, right? Everything is now the same temperature at the end of that experiment. What happened? There was a transfer of energy from the hot object to the cold. Did the hot object do work? No, but 99% of the literature will say A is the correct answer for what is the definition of energy. But if you really dig deep, it's more like, it's the ability to make something happen. This really kind of goes with the person on the couch. Hey, a long day, you're laying on the couch. Get up and take out, I got nothing left in me. I'm done. I'm beat dead. I'm just going to lay here. No, the trash needs to be taken out. Dishes need to be done. No, I'm done. No, done. Toast. Anyway, they can't make anything happen. They can't make a weight go up in a gravitational field. That would be work. They can't turn a shaft that's, resisting the rotation. That would be work. They can't make something hot. That would make it happen, making something happen. But anyway, what we're going to do, this is the first day. Correct, 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 and correct. But I'm going to throw them all out anyway. It's just the first day. Now, a lot of these definitions have mass. Something in this list sounded like mass. Who would like to raise their hand and tell me which one sounded like mass? E. It's the resistance to acceleration. Briefly. It's like, yeah, if you have a large mass, you have a large inertia or resistance to acceleration. Linear or rotate. Yeah, that's good. Somebody else, different volunteer now, for time. Which one of these thinks it's close to time? Go ahead. D. It's measurement of some sequencing of events. Believe me, time to me is the hardest thing to define. You're like, yeah, I'll try to define time later. I've used it and worked with it my entire life, but to define it, it's challenging. Go talk to the physicist. Force. Who would like to give me volunteer for force? Yes, sir. The strength to accelerate, right? Got it. Now these two are the contenders, so we get rid of the ones already taken. And we say one of them is the ability to do work, and one of them is ability to make something happen. Guess what exergy is? The ability to do work, and we mean the force through a distance type of work, the torque through an angle type of work, the mechanical work. Often they say lift a weight in a gravitational field, that's work. Getting something hot, that's not work. Right? All right. So that's really exergy. Now, I'll need a new combination of properties for my property exergy. Well, here's the long derivation, and the bottom line would be something like the exergy, if you want to put it on a per unit mass basis, lowercase e, exergy, is going to be lowercase u minus lowercase u naught. What? We'll get to the naught in a minute, but it's like state zero. State zero, that's the naught. Okay. Plus P naught. Hey, that's subscript 0 again. Yep, P naught. V, I'm going to put specific volume minus specific volume naught, minus T naught, S minus S naught, plus the kinetic energy, which is 1/2 V squared. That's velocity squared, not a specific volume squared, plus GZ. That's the bottom line. That's where we're going. I put this on a per unit mass basis, so all of these are lowercase except for the T, and I think the P in this book uses lowercase p anyway for pressure. But anyway, what do you mean by this naught? Well, you have to talk about some sort of temperature that's our ambient, environmental, exergetic, zero state temperature. Typically 25 degrees C. Been in a chemistry class? That's like, hey, it is 25 C. Everything's referenced back to 25 C. What about the pressure? You think we should use 0 absolute pressure, like a complete vacuum? No, 1 atmosphere pressure. It's just like that. So this P naught, 1 atmosphere, T naught typically 25 C, but read the problem, they'll change it, make it a little different. All right, those are my exergetic reference dead state temperature and pressure. Huh? Well, this is how you evaluate the property. Let's get to the derivation after we talk about it a little bit. So if something comes in where it's hot and high temperature, it has a U greater than if it's at 25 C and 1 ATM. That's the value of the internal energy of the steam, refrigerant, whatever substance I have at the dead state conditions at that known temperature and pressure versus at the current temperature and pressure. Think about it that way. You can get it as function of temperature and pressure. How about this V? Well, what is the specific volume at that condition? Subtract the specific volume if the substance was at the dead state temperature and pressure at the dead state conditions. What about this S? Same concept. The current condition of its entropy, specific entropy, compared to its entropy if it got to be in the same temperature and pressure as the environmental dead state. And then what about this V? Well, it's its current speed, and that's our specific kinetic energy. Think about this. What do you think the dead state velocity is? Well, the person laying on the couch, dead state, what do you think their speed is? 0. As our substance goes to 0 speed. It has no kinetic energy. Just like this, GZ, what do you think Z naught is? You're in the bottom, you're at 0 elevation. This is 0, 0, okay? So we don't even put in the kinetic energy at the dead state and the potential energy at the dead state. We leave that off. So if you're at some elevation, you have some ability to do work. you have some speed, you have some ability to do work. If you have some high temperature and pressure, then your S is going to be defined or can calculate, your V can calculate, and your U can calculate. And if you calculate it all like that, you can get the maximum theoretical, possible, useful work that can be produced. That's Exergy. Now, you want the derivation? Okay, let's get the derivation. That was the bottom line. So here's the derivation. So this is in Cliff Notes. I go fast because that's what the students want. They want to know they can read the book and go slower or slow down the video lecture later if they really need to penetrate. But you start with a system. Here's my system. Think of it as high temperature and high pressure. It doesn't have to be. You can generalize it later, but it's easiest to think of high pressure temperature. You have an exergetic environment. Why did they use the letter ENV? Environment. It's my exergetic reference environment that's around that system. It is characterized by a value of T naught and P naught. 25 C, 1 ATM. Typical values. Now, what you want to do is theoretically ask the question. You're going to let this initial system at this initial state go to some final state. The final state doesn't have to be the dead state, but during that process, it could produce amount of work. During it, it could expand, and that's what is shown here, but it could also contract, but expansion is easier to show here. And so let's say that the final volume at state 2 is different than initial volume at state 1 of my system. What did it do? It pushed into the environment, that exergetic environment. Right away, you're thinking, work. You pushed it to the environment. Integral P dV. That's completely correct. You pushed back the environment. So, but you know what? Pushing back the environment is not useful work. What you really want is you want to separate out, let me get rid of this, what component gets out of the combination of the system with its local exergetic environment and can lift a weight in the rest of the world. Do something useful. Lift the weight, that's the easiest one to think about, in the rest of the world. Okay? So, how do we solve this or do this derivation? Start with the first law, focusing on the system undergoing a process from initial state 1 to final state 2. Does that look like a first law or not? What do we have? Well, you could change the internal, change in kinetic, change in potential energy. I didn't take it all the way to the dead state. That's in the limit. That's when we want the maximum. Just do from state 1 to state 2. Initial state 1 to final state 2. And then what is this term? Well, this is my work. You think about it for a minute. You say, you know what? That work is a combination of boundary work pushing into the environment and useful work which gets it out of the combination of the environment and the surroundings to useful work. Okay, so we're going to replace that 1W by 2 terms. That's probably one of the hardest concepts right there. Now, what about this? Well, a lot of people would just put Q. But you know what? We could put the integral from 1 to 2 of del Q, can't we? It's like I'm setting up for an integration. I really need to do that. So a little foresight on my part. Let's continue. You move to the second law. You write it for the system undergoing a process from initial state 1 to final state 2. So what is this? Change in entropy. What is this? The entropy transfer across TB. Isn't that TB right there? It's hard to see, but what does that B on that temperature mean? The boundary temperature. Right? That boundary temperature could be constant, that makes the integral easier, or it could be variable, makes the integral very hard. All right. But we're going to sum up all of the heat transfers divided by the instantaneous boundary temperature and sum them all up for the process. And what is this sigma right here? Some books use SGEN. It's a little more intuitive. S for entropy, GEN for generation. But this book uses sigma. We like Greek letters. Anyway, so it's our entropy generation term. That is a second law. Both of these are well within your means. What you do now is you take the second law, multiply it by a constant, T naught. Isn't T naught the dead state temperature? Yes, the constant environmental temperature. And then subtract that from the first law. That way I can combine these two integrals. So I multiply by T naught here, I put a T naught there, and I put a T naught there, and then I subtract it from the above equation, and there it is, right here, all done. You see where this term comes from, blah, 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 all that. This is useful work. This is the combination of the heat transfers, and I have 1 minus T naught over TB. All right, I then take this term, which was the non-useful, move it over to this side, and I look, and it's like, you know what? This looks like a change in a property. It's a change in a property called exergy. What is this? This looks like an exergy transfer with heat. This looks like exergy transfer with work, and it's nice because it's 1-to-1. If there's 1 kilojoule of energy transfer by useful work, it's 1 kilojoule of exergy transfer with that useful work, or with that work. All right, and then we have something, it's called destruction. Entropy was produced when we had irreversibilities. Exergy is destroyed when we have irreversibilities. It destroys the ability to do work, useful work. That's what exergy destruction. What's the source? Irreversibilities, friction. Right? Okay. So really, we just got a balance. This is an exergy balance equation for a closed system, and that's it. Notice this one term, 1 minus T naught over TB. Usually the dead state temperature is lower than the boundary temperature that's a little higher. So it's like 1 minus T low over T high. Hey, what does that look like? 1 minus T low over T high. It looks just like our Carnot heat engine efficiency. Yeah. And you're right. It's like, hey, some of these things are starting to dovetail. That looks familiar. All right. Now, what we do to get the property, we got an exergy balance before the property, is we think of, okay, the initial state is state 1, and then later we're just going to drop the subscript 1 in a second. And the final state is in equilibrium with the dead state. So everything goes to like V0, T0, P0, U0, S0. So the final state is the dead state. So the system is in equilibrium with the environment. And then when you have the heat transfer, the boundary temperature is the actual environmental temperature. It's like going back here, where you're having the boundary right here, any heat transfer, that temperature of the boundary where you're having the heat transfer is the dead state temperature. It's like it's including all the irreversibilities within the system. There's no irreversibilities with the heat transfer at the boundary. Okay, so now what you do is say, well, why is this term right here 0? It's not because there's no heat transfer. It's because TB and T0 are the same, so I have 1 minus 1. That's why. All right. We still are interested in useful work. We have exergy destruction. We look at these terms, and we have to work with them slightly. You think about it. This was U2 minus U1. The final state is the dead state. The initial state is state 1, and we're going to drop that subscript and say this is the property at the current state of the system that we're interested in. You do the same thing. So anyway, you re-express what is my useful work. It's this minus delta U minus blah, blah, blah. The minus signs will work out. All of these are going to turn into our property. Expand it out. So we have our dead state, our initial state, our dead state, volume, initial state. Switch them with the sign-ins. What is our kinetic energy at the dead state? 0. Potential energy at the dead state? 0. And so what it is this work useful is all of these right here, and that's simply a grouping of properties. And when you have a group of properties, if you wanted to, you could rename them to a new property, and they did, and they called it exergy. Why is it useful? Well, because if you have no exergy destruction, if you have no irreversibilities, no entropy production, then this is 0, and now it tells you what is the maximum useful work out of the system. And here I've expressed it as on a per unit mass basis, so the property on a per unit mass basis exergy. U minus U naught plus P naught times V minus V naught minus T naught S minus S naught plus 1/2 V squared plus GZ. That was a lot to swallow in 2 slides, was it not? Are you lost yet? It's pretty tough. Pretty tough. So, what are the key equations? This equation. Basically, it's all on cap U's and cap V's. That's basically volume. It's not on a per unit mass basis, but this gives me the exergy of my system. If I divide by mass, I have my specific exergy, lowercase e. You have exergy change. If you're interested in how the exergy changes from state 1 to state 2, you could just do it like this. We've seen these equations, right? And then here's my exergy balance. That's kind of like what we started with the derivation. The exergy change, you have some exergy transfer with heat. That's 1 minus T naught over TB, the integral del Q. The exergy transfer with the work, think of useful work, not pushing back the boundary, and any exergy destruction. I think I'm out of time, am I not? I thank you very much for your attention. Solve problems, read the textbook. If you have questions, I'll be in my office. Thank you very much.